What I plan to do is to spend hopefully just under an hour going through what's new in 14.2 from my own personal perspective. So it's slightly different content than some of the examples in Stephen Wolfram's blog, and more so than previous times I've done this, there's quite a few things that I just don't have time to mention. So if you go to the help system in Mathematica or reference.wolfram.com, and down at the bottom of the page, there's a link to a full list of new features, although they're a little bit without kind of narrative explanation. Right, let's share a screen here so that you can see what I'm seeing when I get the right screen choice within Big Marker. Here we go. And I'll take my camera off here to reduce bandwidth a bit, and hopefully you're now seeing my screen. Let's get started. So, of course, with the Wolfram languages aim to be a kind of common computational infrastructure for all disciplines, regardless of being specialized in whether engineering, chemistry, maths, or data science. There is a little bit of something for everyone across this presentation, and I'm going to gradually sort of move down towards narrower and more specialized areas as we go through. But more so than perhaps the recent releases, there's a couple of headline features that are very much the kind of the big things that I think will be interesting to lots of people. So we'll talk about smarter AI assistants being one of those, and the other is a new framework for data science. We're also going to talk about some infrastructure things, a whole collection of bits and pieces across different specialized disciplines. And then I'm going to keep towards the end, if you haven't already read about this, the surprise of one new computational field for something that is not incremental at all, a whole new field that we're taking on. So let's talk about the smarter AI assistants. It's been several versions now that we've had tools to be able to integrate large language models and their capabilities into computations you do. And we also sort of pioneered the chat notebook of using notebook type paradigms of a reusable document that has inputs and outputs, that preserves a record, but also can be run on again on a future occasion to the chat world, as well as to the computational world. One of the barriers on that has always been that you had to get your own access to a large language model. So you had to go separately to, and you had to pick from one of the many providers. And we tried to support as many of them as possible. Generate a key, pay for that separately, add that into your Wolfram language and application, and then it would work. So for the first time in this release, we're adding Wolfram provided LLM access. So if you have the appropriate subscription with us for your Wolfram language technology, that will just work out of the box. So when you open up and log into Mathematica or Wolfram One or the Wolfram Cloud, whichever is your preferred way of accessing our technology, if you have the Wolfram LLM subscription, it will just all of those LLM functions and the chat will work out of the box. Now, along with that, we've made some changes to the infrastructure for chat. So if I just get a notebook up here, one is that assuming you have access to an LLM, either through us, or you can still use the old technique of having, if you already have a corporate key for OpenAI or Anthropic or whatever, you can use that. You don't have to use us for the chat functionality. But now every notebook is a chat notebook. So without me having to say, start a new chat notebook, I can interact in a chat style through the notebook interface from the moment that I first start 14.2. But we've also added some extra intelligence to the assistants that we've had. So partly that's through improved interface, but it's also partly through smarter tooling and backend. So in the toolbar now, there's a couple of new choices here. And one of those is a sort of inspiration suggestion button. So if I'm in a given context, let's say I'm right here in the middle of this, I'm writing some piece of courseware for students or something about the sine function, I can click the little light bulb and it will suggest something sensible that I might say next. And I'll get several choices here, and I'm not going to think about which one too much. I'm just going to accept that choice, and it's completed the sentence or completed the paragraph or even suggested where my document could go next. Maybe I go a bit further here and say its plot is very recognizable. And the context of where we have the cursor now really matters within this. So if I click the suggestions button now, this time I haven't got the cursor in a text cell. I've got it in a computation input cell insertion point. So it comes up with a sensible piece of code that I might want to insert there, and I can accept that. I could say, well, maybe this wants some options. So if I put the cursor inside the code and click the button, then it suggests some options here. Maybe I want to have some axes labels, and eventually it's, oops, I've got too many brackets there. And there's our kind of synthesized code. So that's sort of contextual awareness of where you are, the kind of thing that you're in the middle of doing. If I select some broken code and select it and click the button, it'll suggest ways to fix the code. There's much more context awareness in the chat assistants. We also have a new interface paradigm for it, because the chat notebooks are great if you are using chat as your way of building up your work or interacting with the system. But sometimes you kind of want an idea and you're not sure if you want it or not. You're looking for inspiration, suggestions, and then you don't want to have to keep deleting things that you didn't want. So we also now have an assistant that sits outside the notebook. So if I click on this, I've got a separate session, but it is still aware of the contents of the notebook. So it knows what notebooks I have open. It knows what's in them. It knows where the cursor is in the notebook. So it's very contextual. Even though I'm now in a separate window, we've got an environment that is aware of what I'm trying to do and how far I've got. I'm going to do something completely different here to illustrate a different point. Let's do something like plot the elevation and around Durham, UK, where I went to college, with a map overlay. So I can ask it to make some suggestion for me here. And oops, I missed the button. Well, that's the trouble with live demos. Something appears to have gone wrong, and it's not recognizing my button click, because I think I typed the wrong keystroke at the beginning. I'm just going to reopen that and try one more time. Otherwise, I will move on. Okay, I don't know what I did to upset it, but the reason I've chosen this example, hopefully it'll do something sensible for me. So it's coming up with some suggestion here outside of my current notebook, which I may or may not want to use, but it's going to hopefully appear in a moment. Thinking. So the reason why I want to show this example is that over here, what you can see is, well, something's actually gone wrong because I've got a library that's got corrupted on this machine, but it's had access to the resource repository. And in fact, behind the scenes, it has access to documentation, help messages, and yeah, something is wrong with the geo elevation data that I'm accessing, which I'm going to give up on that example. Hopefully the example at least shows the point here that we're not just using LLM innate knowledge anymore for using Wolfram language, but its ability to read documentation and things like repositories means it can find things that are even kind of newer than the last time the LLM was updated. And it helps to improve the accuracy of the code that it synthesizes to know that there's an appropriate resource function that could have been used here. I will have to look into why that library is not correct. So it's a combination of a smoother workflow with better interfaces that I have these kind of contextual awarenesses, and it's also all these back-end tools that make it, for the task of writing Wolfram language, much more powerful than before, because it's getting external prompting on helping it to write sensible syntax and get examples. If I ask it for an example in space, it can search the help system for examples that match my description and things like that. So all in all, that barrier of getting started with the Wolfram language, or if you're a light user and you're not kind of familiar with the thousands of things that it can do, the ability to be able to get something done without the high expertise knowledge is much more powerful. Now, my other main headline is part of a general story that Wolfram language has been going through for 30 years, which is that there's many things in the system where we built really general infrastructure, very general data types that are super, super flexible. That if you think back to the list language construct that we've had since version 1, that always been very flexible. You've been able to make a list of anything. You can have a list of numbers or strings, but it could also be a list of documents or images or sounds, and all of these things are very flexible. The downside of that is that there are often things you can do either more elegantly, more automatically, or more efficiently if you are working in a narrower domain where you can anticipate structures that are more appropriate. It's sort of a performance versus flexibility kind of trade-off. So one of those big areas has been working with tabular data, where we've had no trouble working with tabular data for a long time. It's a relatively simple structure, but the tools that we built, all the various sort of linear algebra tools, are very focused on tabular data, which is numbers. The data set kind of infrastructure works with tabular data, but it doesn't assume tabular data, and so it has to do things slightly more complicatedly because it has to worry about whether things are, mixtures of high depth hierarchical data sets and the kinds of very clever things it can do. But tabular data is a really common area of data science. So we're talking about rows and columns that form a grid, the kind of thing that you would do in Excel. And in fact, Excel enforces on you because its only world is tabular. And one of the characteristics of tabular data tends to be that the columns are quite homogeneous, that you will have a column of dates or a column of numbers or a column of labels, and the rows tend to be kind of fairly independent. They're observations. So that's the kind of narrower field that we've now looked at and said, okay, if we wanted to handle that kind of data, how could we do that better? Because it is a big fraction of data science. SQL data always comes out in tables. Spreadsheets and things like CSV files are all basically tabular data. So it's really common. So I'm going to go through here a sort of simplified data science workflow where I'm going to get some data in, import it into the system, clean it and canonicalize it, and then do some computation on it. And it turns out that the framework that we've built is got really important things to say at each stage of this. So first of all, getting it in. There's some well-established formats that are very common in this space, like Excel files, like CSV, or the open spreadsheet format, TSV, table formats, and so on. So if we're really focusing on this area, one of the things we want to do is speed that up. And I thought I'd changed the path for this, but oh, that's set directly, yes. So I mean, I'm just going to import some data here from a tabular, and it's taken 2.5 seconds to bring in 1.5 million rows of data. So I haven't timed it on this. I'm on a Windows machine that's a little bit puny compared to my 2-year-old Mac laptop, but on my Mac, I time that to be about 5 times faster without having to do anything special. Just CSV is a popular format. We've given it some attention and accelerated that by a factor of about 5. In fact, in a minute, you'll see that we're doing even more than we were in that reduced time. So it's not just that it's less time, it's doing more in less time. Now, those are ancient formats. CSV goes back probably before I was born, or certainly somewhere around there. But there are more modern formats that are focused on this kind of column-oriented data. So Parquet being one of those, and so we've added support for Parquet, Awk, Arrow RPC, and Arrow Dataset. And if you start using these more modern datasets, then the same file, the same 1.5 million rows of taxi cab data from New York, has now imported about 5 times faster than the 5 times faster. So that if we can get it in Parquet format in the first place, then we can get it into the system about 25 times faster than previously. And of course, it doesn't really matter that much for something that was previously going to take 15 seconds. It's not a huge deal, but 1.5 million rows isn't that big a data set. So when you start getting to big data sets, then it starts becoming the difference between practical and impractical, when those sort of import times start creeping over multiple minutes just to even get started. And now we can do that in seconds. That's a big improvement in practicality. Now, another part of this is that we want to be able to do better with big data. So data that is not even kind of in the few million or tens of millions of rows, the kind of things that you can hold in memory. We want to be able to deal with data that is larger than you can hold in memory. And there's a new mechanism that is seamlessly integrated in with that, of being able to declare that I've got some tabular data, but I'm not actually going to import it. I'm just going to point to, in this case, an SQL-like database and a particular table within that. And I get an object now that allows me to do all the operations you'll see in a minute, but it doesn't actually do them immediately. It treats them as symbolic operations. So if I ask for something like a selection of the rows in that data set which have country equals USA, I can do that without ever having brought the data into memory. Effectively, what it's doing is a certain amount of symbolic representation and simplification on something that is really an inert object. At some point, we need a concrete result, and at which point I can say to memory, and then it will effectively execute that, and I get my 3 rows. Without the previous way we would have had to have done that is either resort to low-level SQL, and you're having to kind of write code to access the right data, or you would bring the whole data into memory and then throw away most of it in order to shrink the memory footprint back down again. And now we can do these kind of start building up code and operations without ever having to touch the masses of data. We only end up having to bring into memory the bits that survive the filtering and transformations and whatever it is that we're doing along the way to that data. Relatively small, but also a nice bit of convenience is there is a new symbolic representation of data stored in distributed and remote file systems. Basically, it's a package of credentials. So you can set up a data connection object that has the information it needs to be able to reach into the Amazon S3 bucket or Azure blob storage and fetch out information. It's basically a form of import, but it's a way of brokering all of those handshakes and crypto signature type things that protect the data to make it a reference that you can pass around within code to access remote files in these big storage systems. So the headline thing really here is faster import, but actually it's also about scalability, that we're trying to get into this out of core computation space and large storage systems for remote data. Now, what's the thing we actually got in there? You saw sort of passing reference to tabular. The data that I've imported from that Parquet file, it's a new object within the Wolfram language, and it's an object that basically declares that its contents is tabular data and brings, by virtue of that wrapper, a certain amount of automation. So one of those bits of automation is that it formats very prettily. So here is the output of that tabular data, and in the notebook, it will render as one of these table view objects where, even though we've got 1.5 million rows, I don't have to pollute the entire notebook with lots of data here. This data is being sort of fetched on demand as I browse through it, and I have a kind of nice view on what's there without having to have a huge notebook. Now, if we mouse over the top here, and I don't know if that's probably very small font on your screen, so I'll read it to you. It's a little tooltip appeared there, said pick update time. That's the name of the field, which you could see already, brackets date. So one of the things that we're bringing to bear here is that this table has a notion of typing within it. And this is where some of the performance magic is going to come from. And I can ask it actually in a much more formal way, what is the structure of this data? And you can see here that I've got first column is called ID, and it's a string, and there's 1.5 million records in there, and it's taking a certain amount of memory. But we have some very compiler-friendly types going on here, that this column is real 64s, and 2 of these columns are dates. And this is what I meant by it's doing more than just the import. That in that 5 times faster, it's actually parsed all of those date strings that previously when you imported from CSV and you had dates, you would get a column of strings, and then you would have to map date object down the strings to interpret, or interpreter down that column in order to canonicalize it. And that's happened at import. It's recognized those are dates, and those are now dates within the system ready to do date difference or date plus or whatever kind of or selection I want to do on them. Now, one of the things that being able to rely on homogeneous types, and there is a general type, there is a expression type for things where you've got a column that has just a mix of numbers and dates and other things. But where it is quite structured data, that allows us to bring all this compiler technology that we've been using to do type accelerated computation. So as an example of this, I'm going to escape the tabular object. Normal will turn any tabular back into a regular list of associations that Wolfram Language has been able to do for years and years. So it's totally compatible with the code that you have if you need to step in or out of the tabular object, although there's a cost each time you go each way, so you don't want to flip backwards and forwards unnecessarily. But if I just take that column of dates, which did I take? I took the pickup date time. So there's 1.5 million dates, and I am asking a simple question using the old data structure of what is the biggest date, the most recent date within that column. Now, because of the generality of lists and associations, it has to think about every one of those records and say, what is this? Oh, it's a date. I know how to compare dates. What's this? Oh, it's a date. I know how to compare dates. And so, not terrible for 1.5 million date calculations to rank them and find the most recent. But by virtue of this compiler accelerated column type, if I stay within the tabular, I don't need to keep asking that question, is it a date? It knows the column's a date, and it can use a kind of compiled version of Max that knows how to deal with those date objects. And that 25-second operation is now, I can't even put that into words, that's tenths, hundreds, thousands, 8 10,000ths of a second. So about a 10,000th of a second, about a thousandth of a second to do what previously took 25 seconds. Now, dates are a big win, but this is generally true that now, by virtue of having this optimized data structure for tabular data, assuming your data is suitable for that, we can really optimize operations that are being performed on the data set and do, again, things that were maybe doable at small scale but became unfeasible for large data, and now fast enough that they become feasible for even really very big data sets. Right, so we've got the data in. We've got this great representation that's going to be really efficient. There's various things to say on cleaning, some of them kind of fairly prosaic, but in the end, they're important to be able to do elegantly and efficiently. So things like transforming the contents of columns. And we have some utility functions here that are designed to efficiently and in single pass transform lots of records, lots of columns within each record. So what I'm saying here is take those 1.5 million rows of data, and I'm going to take the store and forward flag, and I'm going to compare it to the letter n, because whoever provided this data has used y and n to decide true or false. And I'd rather have this in a canonical Wolfram language, true or false. And there was a pickup latitude and a pickup longitude. So I want to add a new column here called pickup location, which is going to be a combination of those two columns combined into this new column. And we can give as many rules as we want in this transformation. And then in a single pass of the data set, we get a new data set, new tabular out, where if I scroll through this thing, you'll see somewhere here there is our store and forward is now trues and falses. It replaced that column, but our pickup location is a new column that is now a geo position in a nice Wolfram language geo position object, and it probably has some type here in inert expression. Okay, that one isn't optimized. Similarly, we can throw away columns we don't want. Again, in a single pass, I can just say pick off certain columns that we want to get rid of, and they're all gone. We can rename columns, so I could give them more Wolfram language style phrases. And so fairly quickly here, I've cleaned this up into canonical types, owning columns I want, and we've only had to pass through the data set 3 times, once for the transformation, once for the rename, and once for the column drop. And some of those can actually, with a bit of coercion, be made to do in a single pass. Now, one big part of the whole kind of cleaning process is anomaly handling. And things that aren't meant to be there, or values that are out of range, are things that we kind of want to deal with, but we also don't want them to break our beautiful column homogeneity. And so the tabular framework deals with that as well. In my taxi cab data, I'm going to make an almost certainly false assumption here that no taxi journey can be more than 2,000 seconds. So I'm going to replace any durations above 2,000 with missing in the data set. So even though this column was of type, I think it was type real, real 64, it might have been integer 64 in the original, I want to insert some missings into that. And I'm using the transform columns that I showed a moment ago. So we're just replacing the duration column with a modified version of duration. And you can see here now, down here is a missing item where it was out of bounds and we've decided that it's missing. But the type here is still integer 64 on this tooltip. And that's because if we look at the tabular structure, we're treating missings as a special case because they come up so often. We've got a column which is integer 64. It's got 1.3 million non-missing values and 84,000 missings, but those don't change this and force it into some kind of expression type representation that is really general. So we've sacrificed nothing by putting missings in. Now, missings, it's all kind of easy to put them in. It's dealing with them can sometimes be problematic. And a little digression here. This is a typical problem that anyone who writes Wolfram language code ends up having to write fairly trivial but annoying code to get around. I got some data and I want to do something like map a function over that data. And map is nice and elegant, says take the square root of every element of example. But the trouble is square root of missing isn't defined and square root of $failed isn't defined. And so we end up having to make special cases of saying, well, if it's a number, then take the square root, otherwise do something else. And we now just have a really elegant little utility function that we can wrap around any operator or functional expression and map a fail-safe version of square root over that list. And now things like missings and fails gets passed through whatever the operation is I'm trying to do, and the operation is only applied to the places where it's not missing or not failed or other kind of pathological things like $cancelled that might be in there. So it's just a utility function, but I think these little things in Wolfram language that help you to write really readable and compact but robust code are really kind of useful. And I'm going to use it right here by saying, okay, I'm going to transform that duration column from integers into Wolfram language quantities. So I'm doing a kind of type transformation on the column by saying I want the quantity of that number in seconds is what that column means. A bit more canonicalization. Now, this is going to coerce the whole column type. And when we finish here, we'll see hopefully the data set. Duration, you can now see type here. It says duration quantity integer 64 seconds. So the type information is now attached. The column itself still has in it, its display is still just to show the number, but every time I pick numbers out of this, these will now be quantities. So if I did that convert to minutes, it will now just work. But the missing has not ended up as missing of quantity of missing, it's just missing. So it still will be handled seamlessly in all future operations. Now, the question is, what do you do with missings? And there's lots of strategies depending on the context. And we've got this new fairly useful general function for dealing with missings. In the past, the only functionality we provided was delete missing. So you could delete the missings out, or you could delete rows that had a missing, or rows that had a missing somewhere deep within them. But now we have this sort of super function with all kinds of methods to be able to take that data set. And in this case, I'm imagining that the reasonable thing is to say these are sequential. So maybe the best estimate for this duration is some interpolation between the estimate before, the time before, and the time after. That the best guess for filling in this with some actual number would be somewhere in the 500 range. And so that's what this transform missing interpolation does. There's lots of sub options, as you might expect, like the interpolation order and so on. And now you can see that in my new data set, I can't remember, there was 100,000 missings in the data set. They've all now been filled in with an interpolation of their before and after. Actually, I happen to know these taxi journeys are independent observations, so interpolation is probably a bad idea. So maybe I want to do something like a random element or a fixed value, or a random number from a given distribution. There's lots of ways that I could make synthetic data to fill in the gaps. And they're all wrapped up in this transform missing function. If you look at the documentation, you'll find about a dozen methods in there. So we got the data in nice and fast. We got cleanup nice and fast. We're handling missings in a better way than before. In the end, you're doing this for a reason. You want to compute something. And there are all kinds of ways of doing direct operations on the data set. We can do things like select and apply functions, all the kinds of things you would do with data set in the past in a fairly direct way. But in the world of tabular data, there are certain kind of operations now become reasonable that in more general data structures are kind of pointless, because you can't, there's so many cases they don't work, they become just silly functions. So one of those is aggregation. So I can take my data set here. I'm sorting it first, but then I'm going to say I want to find the mean trip time. So I'm giving that a name. It's not a column that's in my data, and that's going to be the mean of the durations. But I don't want to do that for the whole column. I want to do that per vendor ID. So we've split the data into sets of each vendor ID, and then within that set, we've aggregated all of the records down into a single number. So you could have done that before. You would probably have to write 2 or 3 lines of code, and you might even have to think a little bit about how to deal with, how the aggregating function deals with what's in there. That's now this kind of neat aggregate rows function. And the one thing that my business department Excel jockey colleagues have always made me jealous of is pivot tables, which there's a nice little button to make a pivot table in Excel, and you have to write a fairly cryptic 2 or 3 lines in dataset. There is now a pivot table function that allows me to say, what are the rows and columns? So again, we're splitting the data by 2 dimensions now. And then within that combination, so the 0 passenger journeys for vendor ID number 1, find in this case the average. And that's the average time for vendor 1 on passenger 0. I've got a useful little option here to throw an all column on the bottom and right hand side. And so now we've stratified the data in 2 different dimensions, and we can see fairly at a glance the comparison between vendor 1 and vendor 2 in this New York taxi cab data. That vendor 2 tends to be the only one that takes large loads of passengers, so they're the only ones with the minibuses, and vendor 1 seems to be doing generally longer journeys for the smaller passenger set. And we can see the set by set weighting. But unlike Excel, of course, we can scale this to very large data, and the kinds of aggregation we do can be any Wolfram language function. So while mean and total are the kind of 2 obvious ones, and max and min, I guess, also pretty obvious, there's any number of kind of ways you can do of collecting a bunch of records together and making a thing that you want to see that represents that you want to do sliced over each of the 2 conditioning parameters. Also, a lot of the standard functionality has been extended just to recognize what to do with tabulars. So let's get in another tabular data set here, just because it's more amenable to machine learning. I've got a tabular of flower measurements. Well, classify knows how to deal with tabular objects, so I can just say classify that tabular object where I'm trying to pick the species from everything else. So you don't have to start doing drop column species, generate a training set from the remainder, build the classifier, and then figure out how to take a random sample from that and pass it back into the classifier. We can just sample that tabular. We can apply our classifier function to the rows of that new sample tabular to get our 3 predictions out. The visualizations all kind of know about tabular, so I can, again, without having to slice out a column and then plot it, I can simply say, I want a histogram of that data but I'm only interested in the passengers column. And this sort of neat selection syntax also applies to multivariate things. So I could plot, for example, the pickup time versus the duration for the first 200 rows in that tabular. I can take that flower measurement data and now do a kind of 4-way pairwise smooth histogram plot. Hopefully coming up in a second, just by saying I want the tabular object, and this is just a low evaluation. Okay, I think that's going to be unhappy. Let's just abort that, and are we getting the kernel back? Let's just restart the thing, and then we know it's happy. New 42. Yep. This is what I hate about using somebody else's computer for Presentations, you don't know what the quirks of it are. All right, let's go back to where we are. Right. Right, let's just move on from that. The basic idea is that particularly things like visualization commands all kind of recognize automatically how to deal with tabular objects and have a neat syntax on top. So I spent a long time on this feature because I think it's a really important thing that our ability to scale, both in terms of fast import, compiler accelerated processing, and be able to do those things much faster for bigger data sets, holding them more efficiently in memory, but also having the ability to access them out of core, and deeply plumbed in with a lot of the existing functions, plus a bunch of utility functions that make typical operations you want to do really much more elegant and succinct and easy to read the code for, is I think a really big deal for just doing regular old data science faster and more conveniently. Okay, let's go on to a different topic. This is really now a beginning of a story rather than a kind of big framework landing. There's a new basic data type, GPU array, which is another one of these things of taking a specialized area and then packaging it up to make it easier to access. Now, I can't actually show this one live because this broadcast machine in our studio doesn't have a GPU on it. And the whole point of this is to be able to utilize GPU frameworks in a fairly seamless way. So I took these timings on my 2-year-old Mac laptop, which doesn't have much of a GPU on it either. If I had a PC with a big CUDA card, we could expect to see better improvements in performance. But still, you can see the basic mechanism by which it works. I declare an object, GPU array. If I don't have a GPU or that's compatible, this will just fall back to being a good old-fashioned packed array that runs on CPU. But after that, I don't need to do anything special. In this case, I'm just squaring all those numbers and adding the arctanch of them, and the computation happens. But behind the scenes, that data has been computed in a compiled function on the GPU, with the data copied onto the GPU when it was created. So those operations can be potentially much faster. In this case, about twice as fast for this fairly simple unoptimized computation compared to doing this the old-fashioned way of doing that on CPU. So the real win here is if you've got the hardware. But obviously that is a direction of travel of all the computer manufacturers. And when I pluck up the courage to ask for the brand new Mac, then mine will get slightly better as well. Also in performance, as you'll see, there's a theme here going, quite a lot of performance things. The parallel computing tools, which are really about utilizing multiple cores or multiple computers. There's a few improvements here. There's a couple of new basic paradigms. So many of the parallel computing toolkit functions are analogous to existing functions. There's a parallel do and a parallel table instead of do and table. And they split the task up over your worker kernels. They all run in parallel, and then it assembles them back together. So there's two new ones on that. Cases and select for picking elements out of data that match a criteria or match a pattern. Those now have completely parallel equivalents. So I can just say parallel select, give it a bunch of data. That data will be split up over however many CPUs I have available. And then this task will be operated by each one of those machines independently. Now, locally on my machine, that's really just a kind of convenience function, helps us to program more elegantly. But for the very large parallel users, and I know we have some that are running on hundreds of CPUs, we've also made remote kernel launch. So that's if I've got a cluster of unused computers in a lab that I want to connect to and use them as workers for my personal computer, perhaps they're free overnight, or I've got some dedicated cluster hardware. The ability to launch many of those simultaneously is now much, much faster. So before, the time of actually setting your infrastructure up might have taken quite a while, and then it was fast once it was running. Now that remote launching is much faster as well. Okay, let's move to a different topic. I've sort of touched on LLMs already from the point of view of chat and as an assistance to help you code, but they're also useful for writing functional code, for doing things like transforming data, taking unstructured data and structuring it, making judgment decisions for which it's hard to write rules and code for. And there's various commands like LLM synthesize and LLM function and LLM example function and LLM chat evaluate for managing your own chat platforms. So one of the things that we've done there is to provide asynchronous access to most of those functions. So I've got a toy example here to try and illustrate what's happening. LLM synthesize submit is like LLM synthesize. It sends some input, some prompt engineering to my LLM, and it'll get back whatever the LLM has to say. But what LLM synthesize submit does is it doesn't stop and wait for the answer. So at the moment, we have blocking operations that won't move on until the answer has come back or there's been a failure, and then it moves on. And in this little piece of code here, I'm going to immediately go on to print the value of some variable. And then I'm going to do something important, which is, in this case, wait for 10 seconds. But this could be doing things like updating the interface, waiting for more user interaction, doing some other computation. And in the meantime, this submission to the LLM is busy on whatever my LLM provider is, whether that's the Wolfram one or one of the other providers. But I've set up this handler function that says when its task is finished, so when the LLM answers, then in this case, I'm going to set the value of a variable. So what we'll see is when we run this, once I run this, we will get the variable would be printed. This print statement's been hit. It hasn't waited. It's moved on. Res doesn't have a value. Is now doing this important wait where it should really be doing something useful, but I'm just waiting. And the next time I ask for the value of the variable, magically it's been set by this handler function. So this is sort of set and forget. And then at some point when you look to see whether the answers come in, it hopefully will have arrived. And if it's not, then you have to then go off and do something else and check in on it later. So it's all about not having to get these sort of long delays. If you have something big that you need the LLM to do that maybe takes 10, 20 seconds, you don't want your whole code to freeze at that point, or you might not want to. Now, one particular sub case of that is that these handler functions can be attached to lots of different things. You might have a different action happens if the LLM fails to respond or rejects your credentials or something like that. So there's a whole collection of actions that you can add different events to. And one of those is content chunk received. And what this is and let's make a bit of space on screen here, that if you're used to using a lot of the LLM providers GUIs themselves, you notice that the words stream back onto the page. And it's a kind of neat trick for the LLM might take 20 seconds to answer, but you don't feel like you're waiting for 20 seconds because after 3 or 4 seconds, the first bits of the answer are coming in and you're busy reading them. So by the time you finish reading them, the rest has all come in. And content chunk received is one of those actions to say, don't wait for the whole thing to be finished. Every time it's got something to say, do something with that. And in this case, I'm going to append it to my answer. So I'm going to start with an empty list of answers, drop my request to write a four-verse poem, and every time a chunk comes in, I'll add it to the list, and I'm immediately asking to display that. So what we get is this kind of streaming response is now supported within the language. So if you're building your own interfaces and you don't want that kind of nothing with a spinner saying waiting for answer, here's your answer, you want it to come in streaming, there's now mechanisms to handle that. And they also, there are other possibilities that this can be lent to, such as content moderation, where you might want to kill the response as soon as it goes off topic and not continue with the stream and like that. Okay, let's move to another topic, and this is still is sort of fairly abstract algebraic infrastructure now. So this is something that is more for the theoreticians amongst you, either in physics, engineering, maths, those kind of spaces. And it's symbolic arrays, which we first introduced in, I think, 14.1. So for many, many years, we've been able to do symbolic linear algebra. I can take the determinant of a symbolic matrix and so on. But the way that we had to do that was we had to make a matrix of symbols. So instead of having a matrix called M and saying, let's take the determinant of that and have some algebra and know what to do, we had to make a matrix of A, B, C, and D, and then take the transformation of that. Now, in the end, you get the same answer, but it's got two problems. One is the answer may not be in a useful form, and the other is that the intermediate results might be huge, and so it becomes infeasible. So we introduced the idea of matrix symbol that you could declare as a symbol that is known to the system as being a matrix. And in this case, I'm telling it that it's a 3 by 3 matrix. So that was introduced in 14.2, but the only thing it could basically do was calculus. And we've now extended that to include all kinds of algebraic operations, and also across things like simplification and expansion. So one thing we've done is join up the two worlds, the old way of doing things and the new way. So for example, I can take that and now expand it into the old way of thinking, which is as a matrix of individual entry elements. And just to give you a sense of what happens when we do operations on things like that, and I don't want that formatted. Let me make that unformatted so I can actually compute with it. Then this sort of calculation of the inverse of double that matrix times the determinant of that matrix, this expression is pretty big. And this thing is only a 3 by 3 matrix. You can imagine if this was a 100 by 100 matrix, that's going to be pages and pages of computation. Now, as it turns out, that simplifies down to something simple. But now with this kind of array simplification, we can do that directly without ever having to think about the element by element view. So I can now go to the 6 by 6 version, which would be far too big for me to show on screen here. It would be pages and pages of formula. And I can just say for that array, what's the simplification of this formula of that array? And that now simplifies. So this is a feature I know that some of you have been asking for many, many years, finally arriving, and it's core infrastructure that operates across quite a few operations. And in fact, it also works. I don't have to say what the dimensionality is. I can say, well, what if this was an unknown dimensionality array? It turns out this is 2 to the minus n for the dimensionality of a square matrix is the answer. So algebraic simplifications and transformations on objects that are known to be arrays of known or unknown size. And that is also supported now across a whole bunch of calculus, not just, I think it was just derivative that we had before. Now things like surface integration, line integration, dsolve, these all support this. And that really makes a big difference to the use of dsolve for things like typical sort of engineering coupled differential equations. Here I've gone even simpler. This is a 2 by 2 example. In the old way of specifying this differential equation, we would have to spell out the differential relationships between each of the 4 variables of the 2 by 2 problem. So we've got x1 derivative is equal to x2 1 of t, and so on. There's sort of a whole bunch of permutations, a whole bunch of boundary conditions. And the nature of this differential equation is really hard to see. Under this new way of being able to work, now that these symbolic matrices are much more widely understood, we can set up a matrix of kind of weights of these equations, and the differential equation, the underlying equation here, is now really trivial. It's x prime of t is m dot x of t. And if this went to a 10 by 10 version of the problem, this differential equation will get no more complex. The input data would become 10 by 10, but we wouldn't end up with an explosion of equations to debug. So it's really, really good to be able to have really succinct expression of differential equations now over linear systems. We've also got some improved numerical Fourier transform performance that's all about speed. Another performance improvement. But I went a bit dull to go into the details. Let's go to another topic because I feel like I'm overrunning a little bit on time here. Right, graphs and networks. Just a little bit here. Some improvements to graph drawing if you're in the world of kind of flows and relationship calculations or the maths of graphs and networks. And you'll see why in a minute. These are also getting increasingly important within the system because graph drawing comes up behind the scenes and a bunch of other functionality, including the new framework that we have coming. So one is there's just a new symmetric layer embedding that is designed to make sure your graphs are beautifully symmetrical. So all of the embeddings we had before, to draw this graph perfectly accurately, but it was all kind of a bit lopsided. And if you're expecting things to be symmetric, you kind of want the diagram to be symmetrical. So that's fairly minor, just one extra graph layout. But the other is just fairly minor. It's just a single new option called rotation. But that option applies to a whole collection of graph embeddings. So all of these embeddings are now updated with a rotation option. And let me show you kind of what I mean by that. If we take this that you've been able to do for quite a few versions, a layered digraph embedding. So it's a kind of typical embedding for something that's a sort of tree type structure. Hard coded into that layout was the notion that the tree was going to go from top to bottom, that the the top first layer of the graph would be at the top of the picture, and then we would go progressively down the page. And what the rotation option does is allow you to take control of that. So I can say, I want a rotation of pi by 2. I can now make this a left to right layout. So that now multiplies up across all of those different embedding styles for layouts that have a different default orientation for how they grow. And in typical Wolfram language style, that isn't limited to left, right, bottom, top. It's an arbitrary number here. So I can set that to any angle and choose some weird orientation of the way this tree grows from bottom left to top right that happens to suit my presentation, or for some other reason I have full control of that for every one of those. So typical kind of thing where there's one new feature, but it actually affects quite a lot of functionality across a dozen or so different embedding structures. Okay, let's jump domain again. So video, image, audio computation has been a big area for quite a long time. Many years we've had morphological image processing. We've had, in more recent years, lots of machine learning based image processing, and even more recently we've been building out video processing. A lot of what this is about is joining those worlds up. So actually I'm going to do this in a slightly different order, that a whole bunch of commands that used to work only on images will now just naturally work on video. So I can say barcode recognize of a whole video rather than of a frame and get recognition across the video. So it's not like you couldn't break the video into frames and then make a map and pass it over. But for me, the beauty of the Wolfram language is when we've thought all of these interconnects through and just make them just work. So to me, I love it when we see more and more of these kind of integration features. Similarly, in video editing, things like video combine and video join now seamlessly support stills. So you don't have to specify a duration. You can just drop them in and there'll be a default duration for stills to be brought in. And there's some extra transcription options as well for adding subtitles, being able to style them correctly and control language for subtitles, which is a kind of pure video feature. But I want to jump to the top now and talk about, and let's get a, I am missing a video to demonstrate this on, which is going to be a little tricky. So let me just grab one here from, I'm missing 2 lines of code from my notebook. Let me see if I can just grab that from the documentation. Hopefully I stole yes, I stole an example from the documentation. So let me just copy this over into my talk notebook. If you download this, you should have the example in there. Let's fetch this in, and right, here's our video, which is a short snippet of some cars moving. And what I'm going to do is do just a generic video object tracking on that video. So what we're going to do is reach into the frames of that video and look for things that we recognize. And I can control the recognizer and what we're looking for here, but by default, it's going to use one of our semantic content recognizers. And I know in advance, of course, that amongst the things it recognizes from the real world is going to be cars. Now, we've been able to do that for some versions, but what we were doing was thinking about each frame in isolation. We look at a frame and go, oh, there's a car, there's a car, there's a car. And then we look at the next frame and say, oh, there's a car, and there's another car, there's another car, but they had no relationship to each other. And you could try and do some maths on that. But what we have now is an object that is a way of holding that temporal data about image tracking contents that not only recognizes the cars, but tries to maintain the temporal relationship so that when we see this car in the next frame, it's the same car. So this video I could have done before of generating a highlighted video with the bounding boxes that I've just discovered of cars. But when we play this labeling of automobile number 4 will persist from frame to frame rather than jump around randomly. And this object has lots of things we can interrogate about it. So I could, for example, say, when did each vehicle appear? So if something appeared at one point in the video and then disappeared at another, so very briefly there was a person recognized, but only for one frame that it thought it saw a person. But this automobile 1 came in at the beginning of the video and lasted right through to the end of the 1 second video. And we can ask about individual things within that. Say, let's take automobile number 1 and find its position and get a time series for its positions out. So I could plot that over time and see that at the beginning of the video, it was at 512.116, but by the end, the center point of that thing was at 578.44 in the video coordinate system. Or we could interrogate that particular automobile by pulling out the video and track it. And here's a video now that I can scrub through to see us panning and zooming to keep that vehicle tracked all the way through. So anything where you are taking video data and you're trying to understand anything about movement in a video, this suddenly becomes important things. So if you're doing, things like wildlife tracking, or you're doing security type things, being able to track that person all the way across as they walk through a frame, leave the frame and enter another frame, and hand off between different video streams to be able to not get confused as they walk through a crowd of other people, that all now becomes possible through this very general video tracking object. Of course, what you track is the bit that's up to you. Minor, but very convenient. We also have video storage in notebooks. So in the past, when we had a video in a notebook, we've always been able to display, or haven't always, but for quite a while, we've been able to display videos in the notebook, but they were always pointers to the video on disk. Now, that's sometimes what you want, because embedding them in the notebook will make the notebook much larger. If you've got a 2-hour Hollywood movie you want to embed, then suddenly you've got a notebook that's going to be a gigabyte in size or getting on for that. But the downside of having them external is that if you send somebody the notebook, you have to remember to send them the video. And if they don't put the video in the same relative position, then they don't connect up, and they'll have to rerun the code to reconnect the video. Now you can send a single file and video content can travel seamlessly within that notebook object. And actually, even without sending them, just moving files. I've done it so many times where I've done video computations, and you think, oh, I'll file that somewhere, and you don't file the video. And when you come back to rerun the thing or demonstrate it, then I've rather carelessly disconnected the video. Not quite as carelessly as today, where I cut the whole example, but let's move on to geometry. So a little bit here, but I think more important than it first appears. The little bit that we've got, or the main additional, is we're continuing to grow the primitives that are recognized within as geometric constructs. And geometry has always had this sort of fairly direct relationship with graphics. That most things that are geometric you can imagine looking at, and things that you look at like circles and disks and polygons mostly kind of represent something spatial. Adding to that, we've got filled curve and Bezier curve type options. So those have existed for a long time in the system as graphics. So I can make a picture of that. In this case, it's a particular glyph from a font, but that hasn't been something that I understood as a geometric region, and now it is. So I can ask, hopefully, from that. I am having very bad luck today with what is all I know to be the same problem, which is a geometry library that has got messed up on this machine. But I think this will work if I give it another go. No, it's really upset. Okay, well, let's not wait. Let's give that one more go, because it worked in rehearsal. Let's get that example back up again. New in 14.2. And up through to where we were. Oh, incidentally, while we're passing, the presenter tools has had a refresh as well, so that things are based on magnification, which makes exotic typeset structures more likely to be the correct size when you do presentations. That we often have these sort of problems where things like an audio or video, some of the buttons or contents scale differently because they were absolute font sizes rather than relative. But that's a minor bit of cleanup. I'm in the wrong section still here, aren't I? So I was down here in. Let's try this one time. If my machine is really in an unhappy state, I will move on. But the idea is that I can do things like, what's the area of that? and I can pass it into other kinds of calculations. No, it is unhappy with doing this. Let's not skip those. That the key thing is that geometry is our way of describing the real world to other kinds of calculations. Now, since the filled curves and Bezier curves were really invented for engineering industry to do things like describe the curvature of a bodywork on a car without breaking into straight line segments, what this is really doing is helping to join up the world of geometric computations with the world of CAD systems. So it's all very well to be able to import something from a CAD system, but if you can't actually compute with it, then what's the point? And this is filling out one of those large components that was missing before of all of those primitives. Now, one other thing in the geometry space, if I dare try and do it, is that we're joining the geometry space up with molecule. So we've got these chemistry frameworks for being able to compute things like the 3D bond angles of this kind of thing. There is now a way of turning that straight into a mesh for the geometry system that is effectively the surface area of that molecule once computed into 3D space with, and we've got in the biosequences things like protein folding to be able to figure out what that 3D space is. Now, what surface means depends on the physics and engineering that you're trying to do. So this is, while it's got a default option of just make a mesh out of that, there's a lot of controls over that. I can give some kind of method controls and levels of parameterization. So here I'm having a version of that molecule that is kind of taking a much broader view of where the perimeter of that is. But that's now in the geometry space. So hopefully if things are working here, I can work out the volume of that molecule in whatever the coordinate system is. I could find the nearest point in 3D space, or I could integrate some function over that within the shape of the geometry. But I'm going to skip that and show the more exciting example by moving on to PDE modeling. And there's a story here I've been telling for some years that I will repeat again for those who haven't been a regular on this webinar. So within the PDE space, we built a very nice finite element system for being able to model fairly arbitrary partial differential equations. And that continues to get under the hood improvements. But one of the things we've been building out for some years now is a symbolic language that sits on top of that, that elevates you above having to describe all of the details of the exact partial differential equation that represents Stokes flow or stress modeling in elastic materials and all of these things. You can just talk about the thing in terms of sort of physical world descriptors. And one of the new to the collection now is a collection of improvements to magnetic and some new magnetostatic modeling components. So, for example, if I took that molecule I just had and I wanted to treat it as a bar magnet, as a kind of static magnetism modeling problem within a sphere, then I can talk about that at a much higher level. I can say that it's going to be a member of that model that I just created. That's actually supposed to say ATP. It's a magnetostato potential conditions, so some boundary conditions on it. I'm using the geometry to talk about the space I'm trying to solve for, in this case, a ball that's wrapped around it. And here's my PD component. So I'm never getting down into the, the del squared prime kind of just trying to describe magnetics. Built into that is access to materials. I'm not actually using it in the differential equation, but I am in terms of the visualization here to say, let's imagine it's visualize it as if it's made of iron. And here now is that exotically computed geometry shape that came out of the chemistry bond angle calculations. And I'm treating that surface area as a bar magnet and just simply solving the static magnetism that the flux that would form around that erratic shape. So it's being able to, this whole geometry framework is about being able to move smoothly from the world of kind of describing things or discovering shapes through to the world with calculating them in a seamless way as possible. Okay, we're now getting fairly specialized. This is, unless you're in astronomy, either as an amateur or as a professional, these are probably not so interesting, but we're always filling out these kind of more specialized areas as well. And astronomy has been one that's been building for a couple of years. And we're adding basically one new function here, which is find astro event. But like many of these super functions, it wraps up lots of functionality. So at the top there are a whole list of astronomical events that one might be interested in, like about equinox or conjunctions. And of course, our system includes data on many thousands of astronomical objects. I'm going to pick some familiar ones here for demonstration purposes, but this scales up over really quite a large amount of operations and objects. So what I'm saying here is I want to find an event to do with the separation between Jupiter and Saturn, and I want to find the global minimum, so the closest separation between those two planets in the time interval of the year 2020. And hopefully if we compute this, we get here now our answer that in a very precise way at 6 seconds past 6:21 on that date is the moment when those two planets were closest together. And we could use our existing functionality to say what would the angular separation of those be as we look at them from Earth, or we could actually get a picture out to see, let's see that moment in time, and there's Jupiter and Saturn in a zoomed in star chart calculated from this event. But it's a big collection of events over a massive collection of objects, all to very precise time. And remember, in astronomy, we're also having to deal with what does time even mean, because you have to talk about time at target, time from the observer, and kind of relativistic differences depending on whether you want to take in relativity or not. Okay, I promised you a new field. So this is our new domain, something that we've never taken on before, which is game theory. And game theory is used a lot in economics. It's also a popular topic to study in education. And it was, I believe, invented basically in the Cold War years to answer questions to do with nuclear strategies. And they basically deal with the question of, if you have a game with certain payoffs according to your actions, and you and your opponent both have enough experience of each other to know what your strategies are and can optimize your strategy based on either knowing through spying or knowing but through observation what your opponent's strategy is, what's your optimal strategy that you would pick. And we basically covered all of the core functionality of classical game theory. There are other kinds of game theory, but classical game theory is made of matrix games, which are simultaneous games, and tree games, which are turn-based games, also known as normal form games. So here's the classic example to illustrate this. We have a game theory data function that has a whole bunch of standard classical games that you can query straight out of the data, so you don't have to code them up. This one is incredibly simple. It's defined by a bunch of matrices, but it's slightly easier to see if I show it in a data set here. And what this represents is two players, player one and player two, who can either cooperate or defect. And in the scenario of for those of you who don't know it, the prisoner's dilemma, you and I are both prisoners. We've just been captured, and maybe we've been conspirators over something, and we've got a slightly corrupt government who wants to send us to prison regardless. And we are separated in interrogation. Well, we've talked about this in advance. We know there are two strategies. We've got a story, which we can both stick to. That's cooperating. And if we stick to the story, we're going to get sent to prison anyway. But because they couldn't prove anything, we get 1 year each in prison. So we get a -1 payoff. However, I can cheat on you, and I can tell the interrogator everything, and I get to get away free. I don't go to prison at all, but you go to prison for 3 years. You can do the same to me. So your defection payoff is -3 to me and 0 to you. But if we both defect, then we're both worse off. We both admitted to our parts in it. We both go to prison for 2 years. So you can add this up fairly quickly and see the worst strategy collectively is for us to both defect. But that is a deliberately constructed game to show that that's not actually the strategies we played. So in this framework, we've got various visualizations. So here's a pictorial way of showing player one and player two and the payoffs as bar charts. There are different visualization. I'll show you a couple in a moment. And then we can compute with that and say, what's the best strategy? And the way to read this is there is one collection of strategies. So there's only one solution to this problem. Player one strategy is to have 0 probability of cooperating and 100% probability of defecting. And so is player two. So even though if we stuck to our stories, we'd be better off, because neither of us trusts the other, and the other is incentivized to turn on us. Our only best strategy, knowing that, is to turn on each other and take the non-optimal collective strategy. Now, these things can get much more complicated. So here, for example, is a 3-player game with multiple payoffs between 3 different players. There's different styles of visualization. So here's the same thing shown as a split square problem with a different orientation. And sometimes these games have multiple strategies, and there's other various properties, but that's the basic idea. And tree games is the same kind of idea, but in tree games, they're turn-based. So there is a player 1 and a player 2. So there's a specification of the game. Here it is visualized, which makes it much more understandable. Player A goes first. They might take choice 1 or choice 2. And then depending on what I've done, player B has choice 1 and choice 2, or their choice 1 and choice 2, but the payoffs are different depending on which, route we went down. And these things, again, can get arbitrarily complicated. So here is a richer game where player A not only has a choice that affects the payoffs, but they actually decide who plays second. So player A can choose branch 1, where player B will go next, and then player C gets to go, or they can choose branch 2, where player C gets to go next and player B gets to go, and then depending on their choices, there's a whole collection of different payoffs. And as I said, these things can get arbitrarily complicated. So if we look at the strategies for that, we actually have lots of different solutions that are all equally optimal. If I visualize one of those, we can show the solution here as a map. So we have my very small probability that I should pick B just to keep everyone on their toes. But my main probability is I will pick the C as the player to go next. And so if we go down the main probabilities here, you see that this is the payoff we're going to end up most of the time. But if player A does choose B, then player B's best strategy is to go down their option 2. And again, there's lots of different visualization choices. Because these tree games are essentially all graphs in the end, that whole graph layout framework, including things like orientation, rotation, now come to bear, so we can lay these different trees out however we want. And again, they can be complicated, multi-turn, multi-layer things. This is the classic Monty Hall game show problem posed in the conceptualization of game theory, so we can then compute those optimal strategies of should you swap or stick with the original door that you opened in the game show. So there are other kinds of game theory, but within classical game theory, basically everything you want is built in there and integrated in with everything else in the system. So we're a little bit over the time I promised. That's the tour that I want to give you. I do encourage you to read Stephen Wolfram's blog that covers a lot of the same material, but he has different views on what's important and what's neat about the functionality. But it's quite a long read. And as I said, if you go to the help system, down at the bottom there is a link, what's new, and you'll get a feature by feature list, and you can see some of the things that that are the kind of things you'll find things in there. Certainly I have got functions in there that I totally love because they make me as a hardcore everyday Wolfram language programmer, utility functions that make the language more elegant, but just didn't seem interesting to talk about in a 1-hour webinar. So do browse through that list to see what else is new down at kind of individual function level. So that covers all the things that I wanted to show, and I'm just going to now turn to the Q&A and see if any questions have been left for me by our team who've been busy answering as we go. Could you be kind of okay? The data sources, yes, there was some path to something on my computer. Oh, yes, that yes, I can make that available. That's the taxi cab data. I actually stole it out of Kaggle, but I can certainly make that available, or the Kaggle link available. I think it's under open license under Kaggle, so I think I can just post that through our team, so Jamie can add into the questions how we're going to distribute that to attendees. But if you send a question in with your email, I can certainly get an email to you on that. I'll just end by summarizing really what we've seen here, which is the whole LLM kit and its smart assistant, particularly for light Wolfram language users, is a real improvement in usability. And the data science framework, I think, is the big thing for tabular data, are the two headline things. But hopefully there's something for those who are not in that space as well, across the collection of other bits and pieces. Oh, sorry, I've got a couple of questions. Yeah, I'm afraid, Eric, asking about what the roadmap is for the differential equation framework. I have not been following the development plan for that. That would be a great question to bring back in next week's deep dive, where do we have Oliver in that, who's the lead of the PD group? But certainly that
we
person
do.
will know.
Yes, Oliver will be there.
Well, Oliver Rubin-Cohen, who's coming back next week, is absolutely the expert to ask and could probably answer that question for an hour on its own. But I'm afraid I don't know. Will there be GPU support for LLMs in future? Well, okay, so there's several bits to that. The LLMs at the moment that we're doing are essentially all going to external providers. So whether you have a GPU or not is kind of irrelevant, because if you're using OpenAI as your LLM provider, you are sending the actual LLM bit of your query to them to process on some massive infrastructure and send the answers back. We run ours in private infrastructure, so we're not passing those queries on to third parties, but you are sending them to us to process those LLMs, and we're running I think basically GPT-4 infrastructure in a kind of private Azure instance, but it's still being processed by us with the appropriate GPU accelerated infrastructure. Now, it is possible to connect local LLMs into the framework, and they're where what infrastructure you're running them on matters. But I think most of those are GPU accelerated pretty much automatically if you have them. And it's worth saying that mostly those local LLMs are not powerful enough to do chats-like things, but they are powerful enough to do some useful things like data restructuring or kind of simple decision making. They just aren't very fluent when it comes to sounding like a human's written them. Whether that's changed by this claim that the new Chinese model that came out a few days ago, Deep, I've forgotten its name, which claims to be fully open source and will run on modest infrastructure, makes it feasible to start doing proper chat locally on your own servers. A little bit soon to say. We're busy investigating that and whether or not that introduces new open options to us. But it would matter there. But the examples I've seen of people who claim they've got the open source version running locally, it still requires reasonably serious hardware. It's not laptop or desktop PC kind of hardware you want. You do need kind of server grade hardware, but not necessarily masses of infrastructure. Yeah, so how is the smarter AI different than the Wolfram GPT on ChatGPT? So the main thing here is, and I don't know how much we're going to be porting this back to the Wolfram AI, but it's the tool plugins that we've built in so that when you make a query to the LLM, it has built into it already tools to be able to read things like the data repositories and the function repositories and the neural net repositories. So we've got a big, if you remember in 14.1, we introduced semantic index, which allows you to index content and do a fast vector database search for things that are semantically similar. And so we're using that kind of infrastructure behind the scenes, and we've indexed and ingested all of the kind of Wolfram content. So documentation, repositories, things like that. Examples. I don't know if we have a bunch of community posts and things in there. So it has access to a lot more material to be able to go and look something up that can help inform its answer. I would hope that will also end up backported into the Wolfram GPT, but this in the end is our kind of primary focus going forward, is to make sure that this built-in assistant is really the very best way to get writing Wolfram language code working. Oh, another useful thing to point out about the backing with us as well is that it allows us to monitor performance of new models as they come out and switch them without you having to worry about figuring out which is the best. So at the moment we're using GPT-4 type infrastructure, but in our benchmark that we publish, if you Google Wolfram LLM benchmark project, you'll see that the new model that came out of China a few days ago actually performs marginally better on Wolfram Language. So if it makes sense for us to switch to that infrastructure, then your Wolfram Wolfram LLM toolkit subscription will simply use the better model without you even having to do anything. Whereas if you doing things directly, you now have to think about switching to whatever the model is and keep tabs on that. Is it possible to track an arbitrary point in a video? We have image key points as an element. I have not actually. I want to hesitate before saying yes, because I have not actually myself tried using image key points with the video tracking object. But in theory, that would be the way to do it. Is you're either pre-processing to accentuate the feature and then using something like image key points to pick it out, or you're recognizing something that matches that. So another approach would be to train a semantic recognizer on whatever that point is that you think is interesting, to recognize it and then track the recognizer through the thing. But if you've got a point that's changing in a changing scene, then when is a point not the point is an open question. So that's why, it might be a key point now, but later if it changes color or shape, it might not be recognized as the same thing. Whereas at a semantic level, a car that rotates is still a car. So you have to think about how you're doing it, but there are ways to do that kind of thing. I missed it, but transform missing, is it possible to replace missing elements from one column based on multiple other column contents? Let's just get the documentation up for transform missing. And I do not recall. You can certainly use the transform columns in order to make an additional column that you can then do transform missing. You can just then start doing anomalies on. But what do we have here? We've got tab spec, column goes to spec, and spec allows us. So we got these things like mean, median, mode, random element, interpolation, automatic, type specifier. No, I'm not seeing at this point support for an arbitrary expression within that. So at the moment, the transform missing is based on missings in that column, but the other function that I showed would be the way that you would transform other columns to decide that it's a missing or it isn't in the first place, or to not for missing out. You would write your own code that says transform missing. Well, you would say if it's missing in that column and some other conditions, then do the following to it, otherwise do this to it. So you wouldn't use transform missing, you would use the transform columns operation, I think, for that.